Observational evidence of the Big Bang. Of course, the very first piece of evidence for the Big Bang was Hubble's observation that the universe is expanding. And it was that observation, that discovery, that led to this idea that the universe had a beginning. And then that led to the Standard Model, this idea that the universe began very small and very hot. And if the universe began small and hot, then we could make some observations that clue us in to those early conditions. In the 1950s, I want to say, I could be making that part up, Alfred Herman made some calculations about the conditions early in the universe, and then extrapolated, because they know that as a gas expands, it cools. And so as our universe expands, it also cools. And from that, they were able to determine what the temperature of our universe should be today. And they calculated essentially 3 degrees Kelvin, that is 3 degrees above absolute zero, should be the temperature of empty space. Well, these guys in the 1960s were working at Bell Laboratories, and they were using this bizarre looking thing. This is a microwave antenna that was being developed for communications. And there was some static hiss in the background of all their signals. And they tried all sorts of things. They looked for, a local source, like, an engine or something like that. Nothing. There were pigeons living in there. So they shooed the pigeons away. Turned out they were homing pigeons, so they all came back. Next part's kind of sad, so they tried killing the pigeons so they wouldn't come back. That didn't help. Then they thought, well, maybe it's the pigeon poop, because the entire inside of that horn was coated with pigeon droppings. So they cleaned it out. That didn't help. And it was when Wilson, this is Penzias, Wilson was at a conference and heard about some folks at, I want to say Princeton, trying to build a microwave antenna in the hopes of detecting the signal associated with the temperature of the universe. And that's when he realized that's probably what we just did. And it wasn't any of these other things. So it's now called the cosmic background radiation. This is essentially the remnant temperature or the remnant heat from the Big Bang. And based on the wavelength that they were detecting, they could calculate the associated temperature, and it was in fact 3 degrees Kelvin. And it was coming from everywhere in the sky. That's what this picture is showing. This is a microwave image of the universe. And so all of that signal that you're seeing in there is the heat from the Big Bang. Then in the 1990s, we sent up a satellite called COBE, which stands for Cosmic Background Explorer. Now, what Wilson and Penzias observed was essentially one wavelength. COBE looked at all wavelengths. Blackbody curve, that's this graph. It's a graph of brightness on our vertical scale versus wavelength on the horizontal scale. So what we're looking at is this idea, okay, at a short wavelength, signal was that bright. Go to a longer wavelength, signal's that bright. And so on throughout, the entire spectrum, measuring at each and every wavelength how bright is the signal. And what you're seeing on the graph are these little black squares, that's the actual data, and then this red line, and that's the predicted curve. And as you can see, all those data points fit on that curve. And here you see the more accurate actual temperature, 2.736 degrees Kelvin. We've rounded to 3 degrees in the previous slides, but that's the actual temperature. When this graph was first shown at a conference, the people in the audience realized how powerful it was, and it actually got a standing ovation. I don't think any other instance of data getting a standing ovation has ever occurred. This was the clincher. This was the one that showed, okay, that microwave signal that Penzias and Wilson picked up, that wasn't some fluke. Okay, that probably was this data point. So they found one data point. COBE found all these others. And so this entire curve of data shows that the model was correct. Later, we sent up another spacecraft called WMAP, which stands for the Wilkinson Microwave Anisotropy Probe. There's a word for you. Basically, this did a very detailed observation of the cosmic background radiation. And that's what the picture is below. That's the WMAP image of our universe. And it basically found two things. One, that the cosmic background radiation is isotropic. So that basically means the universe is the same temperature everywhere. But it also found very small fluctuations. And that's what the different colors are showing. And that's a good thing, because the cooler spots are where stars and galaxies would form. Because if it's cooler, then gravity can take over. So WMAP showed us both that our entire universe is essentially the same temperature. These small fluctuations, we're talking about, 0.001 Kelvin differences. So very, very tiny, tiny temperature differences, but enough to provide the seeds for stars and galaxies. So I'm thinking it's the blue spots or the cooler regions on here. I could be wrong. But looking like the structure of our universe, that looks correct. And so these are the places where you get the galaxies forming and the stars forming and what builds up the structure of our universe. So there is all of this evidence pointing to our universe having a beginning.